So I'm very glad to be here. It's a great conference. From the start, I have to say I tread new territory here. I studied philosophy a while back, but lately I've been only giving talks about experiments and data and about well-researched stuff. So by giving a philosophy talk, I absolutely go into new territory for me, but I will try to present my questions and the answers I think I could find for myself for these questions. In the worst case, it will be a talk with nice explanatory pictures if it doesn't bring anything new, I hope, at least. Okay, so when I thought about giving a talk, so what I've been thinking about is the nature of causality, and especially causality in quantum physics. So when I thought about the many worlds interpretation, of course, the question was, how does causal explanation work in the many worlds interpretation? And this naturally led to the Bell theorem, because you could say that this deals with how different interpretations try to deal with the Bell correlations. And in particular, there is this single world assumption in some or other way present in Bell's theorem, and I asked myself the question, okay, what is exactly the function? How does it help to deal with Bell correlations? How does it resolve the contradiction? And also, what are the different ways in which different variants of the many world interpretation tackle this? Is it just, do they all do this in the same way, or are there differences? And what causal stories do they tell on the way? Is this also the same? Is it just unique or not? Probably it's not unique, as you can guess. And the outline of my talk will be, I will just introduce really quickly dialectic acyclic graphs as a visual representation of causal relationships, which probably everybody know, but just to be on the same page, to know the language, the graphical language of my talks. Then I will, from this perspective, briefly sketch Bell's theorem. And then I will go through different variants of the many worlds interpretation and try to sketch the causal stories they tell. And finally, I will propose a really tiny, itsy modification of how one could express or specify the single world assumption in Bell's theorem. Okay, so DAX stands for dialectic acyclic causal graphs, and the scenario we have is we have sets of events, so A, B are random variables, and the notion of causality we're talking here about is a statistical notion, I would say. So it's about relationship between sets of events at A, at B, at C. And a causal graph just draws arrows, so this is an example for causal graphs. It's supposed to be acyclic, so there should not be causal loops, and it's directed. So causal relationships are not just binary, are not symmetric, but they are asymmetric relations. And now one can discuss fundamental assumptions in the Bell theorem, for example, Reichenbach's principle. It says when I have a correlation between two such sets of events, which means that I have a distribution of them which doesn't factorize, then this requires a causal explanation, and there are two ways in which this causal explanation can be provided. Either you say there is some direct causal connection, or you have a decorrelating common cause, which just means that conditioned on the events from this cause, this distribution factorizes. Then you could say it explains this. So this is the notion of explanation. And also, using also the same language of DAX, one can formulate other principles of Bell's theorem. So for example, if I have some temporal order, then I can define a causal error, which means, for example, I can forbid certain types of causal connections. I can forbid retrocausal ones, for example. If I know that, if I have a notion of temporal order, if I even have space-time, then I can define a partial temporal order, which, for example, in special relativity is the light cone. Then I have a past and a future, and then I can formulate the principle of relativistic causality, which means the causal past of any event has to lie in this past light cone. So this would forbid causal relationships like this, for example, of events outside the light cone effect causally influencing my A. And okay, and finally I can define something like free choice, where I say, okay, in my causal story, there is one set of events which is free, and that means that it's not caused by any other events which are relevant for the explanation. So, admittedly, this can be somewhat a fuzzy criterion, but it just means, okay, of course, this also works in a deterministic way, so it does not have anything to do with indeterminism. It just means that for the causal explanation at hand, there should be no relevant causal connection pointing to events that are considered free choice. So now we can write diagram for Bell's scenario. So the basic ingredients, we have two sites, site A and B, with two random variables. have observations and settings at each of the two sites. We take for granted now that we have a notion of space-time there, and then we have uncontroversial causal connections. So you can think of these sites as magnifying glasses. So actually, I mean, these are supposed to be really compact size in this sites in the space-time. So there's different temporal order then. So you have the uncontroversial causal connections between settings and observations. And then we can add the light cones, and we have some source. It's a lambda. It can be source where I set settings. It can be unseen settings, which then commonly referred to as hidden variables. And then in principle, this can have causal influences on all these other random variables, but then we add free choice, which forbids action on the settings. So we assume that the settings are chosen freely. So the causal influence on the settings are not relevant for the causal explanation of Bell's theorem. And then if we set this up, and then we can generate correlations between all these random variables, and in particular, quantum mechanics is an example where we can generate such correlations. And Bell's theorem said that when you look at these correlations, actually you look at a conditional distribution, then this causal structure, which is represented by these arrows, is not sufficient to explain this in the sense of Reichenbach's rule as I presented. So like a short-term formulation of Bell's theorem. My go-to version of Bell's theorem so far was the one presented by Wiseman and Cavalcanti in 2015. Which looks more or less like this. So you have here the things we already talked about. We have the relativistic causality. We have this no retrocausality, Reichenbach's principle. The conjunction of those two yields something, an intermediate principle, which is called local causality. So if correlated events have no causal connection, then there is a common cause in the Minkowski path. So it's not just path, it's the Minkowski path. This comes from this light cone thing. And another thing, as Wiseman and Cavalcanti have put it, is the agent causation. Basically, that the setting is the cause of observation and not the observation the cause of setting. And actually, nothing is the cause of setting. But you need this. This is the minimal formulation you need. And then you look at the conjunction with this, and then they have some single world assumption, which I mean, they call this macro reality. They have a formulation for this. But they don't explicitly say how the single word assumption actually works, but you add the conjunction with it, and then you get a contradiction with quantum phenomena. And then, okay, we all know. So actually the aim is to show that operationalists tend to favor in some sense, to deny Reichenbach's principle, therefore get rid of local causality, and thereby resolve the contradiction, while realists, like typically Bohmians or GRW theories, deny relativistic causality and thereby resolve the contradiction. And of course, one can deny free choice. That would go in the direction of superdeterminism, or the causal error, which would be retrocausal theories, and so on. And what is now the intuition that we have now the big set of worlds interpretation. And looking at this structure, what they better be doing is preserve all the rest. So it looks from this structure that if you deny the single world, then you should be able to consistently held the set of all these other beliefs. At least it isn't excluded by Bell's inequality. So this is then my question. I would like to understand how these different versions of the many world are able to resolve this contradiction, keeping intact all these other assumptions. And Wiseman and Cavalcanti formulate, so the single world assumption, they call it macro reality. It's called an event observed by any observer is a real single event and not relative to anything or anyone. To me personally, this was never clear how exactly this now comes to the resolution of this contradiction, and therefore let's go into the detail and look what the different interpretations do. And we'll start as a warm-up with the de Broglie-Bohm pilot wave theory, which is maybe not technically a many worlds interpretation, but it's been called a many worlds in denial, at least. It's a contentious claim for sure. So remember, this is our Bell's theorem, our scenario. We have the causal story, and we have the correlations which we want to explain. So, thanks. So, we will always start with the initial state where we have Alice and Bob in a ready state, or not having measured, and in this case they have a correlated state of some internal degrees of freedom of some systems they have. And in the case of Bohm, it's actually enough not to talk about the observers. We'll just talk about the spatial wave functions of those two systems. So transition, I think of the setting as orientation of a Stern-Gerlach magnet, and the transition from setting to observation is, for me, already basically in the moment of the separation of the wave packets due to the Stern-Gerlach magnet, because this is the moment where the action at the distance already happens in Bohmian mechanics. So when A measures, what happens is, so while here the spatial part of the wave function is taken outside of this correlation, what the Stern-Gerlach does is it separates a spin-up part and a spin-down spatial wave function which have just disjoint supports. And now the position of the particle XA is a real ontological thing, and it has a real single value, and it either lies in this or in this component. And if, for example, it lies in this component, then simply the actual value of the wave function evaluated at this position becomes 0, and it multiplies this part at Bob. And then if B does the setting, then from the guiding equation of B, this part of the wave function is multiplied by this number 0, so it plays no role in the guiding of particle B in the separation at the Stern-Gerlach magnet. Therefore, deterministically, for sure, the particle of Bob will also end up in this upper part. And already for Bell correlations, of course, what is important is that if they measure different settings, so if, for example, Bob measures X up and down, that there I don't have a correlation, and yes, I mean, I don't have a correlation, and I mean, this is the nature. Bell correlations are not just, that's an important point, it's not just a correlation between the outcomes, it's the conditions in the settings, you have to see different correlations. So already in the story I told, I used a preferred foliation because I said when the moment the particle ends up in one wave packet at Alice, the moment this other guiding equation part is multiplied by 0 for Bob. So I talked about instantaneity at space-like separated locations. So I, in fact, used this preferred foliation like this, and in this preferred foliation, I had such an action at a distance causal relationship. So, of course, I mean, as everybody knows, Bohmian mechanics has this action distance, this additional physical mechanism which explains the correlations between A and B, so it violates relativistic causality. Now let's go to many words. My favorite many words interpretation is actually the Baire interpretation proposed by Barry Lower and David Albert. I find it completely cool. And so I won't even talk now about both states, because I think for this it's completely enough to just talk about just one observer measuring a superposition state. So what happens is the observer becomes entangled. So there's a superposition of the observer having measured up and the observer measured down. And if you look closely at the state of the observer, there's a similarity between these two states. So in both of these states, the observer thinks she measured a definite result. So you could write the state like this, and then this factor out. So in this sense, while there's nothing definite here, still the observer thinks there is something definite here. So this, in my opinion, boils down to simply saying factually there are no correlations. There's just an illusion. There are no Bell correlations. So it looks like delusional observers cannot properly interpret their mental states. So the single world assumption is violated in the sense that the Bell correlations F are simply not a fact. And actually something similar, I would say, happens in local branching, as for example, Kai showed us, or also I heard it from Gilles Brassard, for example. Where you, so again, we have our initial state, the correlated internal degree of freedom, the observers in the ready state. Let's now say that A and B time, and we have the local branching. So we have 2 words for A, 2 words of B, but there is no factual correlation, I would say. If I clearly understand this theory, on the level of the universe, there is no correlation. So also this denies, I would say, the factuality of Bell correlations. And only if I go to the common future at a site, where the reports from A and B meet, I have non-problematic direct causations to the site, and then because of the unitary evolution of Schrödinger equation, I have then this correlates itself into 2 worlds at C, and then I have a factual correlation there, and this I call then F prime, and then I had a discussion with Kai about this. So to me, it seems there must be some direct causation going in there, after all, because if it could be just a common causal explanation, then I think it must have also worked here. So what is different between this moment and this moment is just that the direct causation is allowed. So for me, it seems in some way there must be, and also the information of the settings must come here, and this from this there must come, in my opinion, as I see it, at least direct causation there. But if it's really there or not, the point is that you have the factual correlations only after the signals of A and B meet locally. That's the correlation of the report, of the local reports. And you could say in this sense, yeah, the violation of the single world assumption works in the same way as with the Baire theory. The Baire correlations are not a fact, but the reason is slightly different. Then the last thing I would look at is global branching, at least in Lev's version, as I try to reconstruct it. So again, we start with this standard setup of Bell's theorem. We have our ready state, and then if A does a measurement, I already have the global splitting. So such a global splitting that the macroscopic state of B is still in both worlds, so then identical in the sense B does not split, but the microstate already splits at this moment. And then if B measures, let's say, the same setting, then I get the correlation. Basically the observer then splits into the two worlds, which A already, so B then splits into the two worlds which A already separated. So it seems to me that on the level of the world, the correlations are embraced, because in the world description, you already have the correlations here. So if they measure different settings, you actually have then a splitting into 4 worlds. So from the perspective of the world, I would say the Baire correlations are there. And already in the story I told, there was again a preferred foliation, because I said the moment that A measures, the microstate of B splits. So again, I talked about instantaneity and two space-like separated locations. So this had a preferred foliation. And I mean, there's effectively action at distance, as Lev also said. On the level of the world, you have action at distance. I put it in yellow because I would say it's not the same level of a fundamental ontology as in the Bohm case, but it's on this level of a higher description. So the Baire correlations are only effect on the level of a world. So it's like a different explanatory level. So here many worlds is the many worlds approach allows one to somehow have different levels of explanatory description. So also thanks to David Wallace to explaining this a little bit to me. Also that this foliation is more convention, because it also doesn't really matter what kind of foliation A chooses. It's important for speaking what happens at B, but in the end, any foliation, I mean, the test will only happen when they come locally together. So there is, in this sense, a direct causal influence, violating relativistic causality, but only on the level of the world. So it seems to be that the single world assumption deals with the factuality of Baire correlations, and when one looks at different formulations of the Baire theorem from different authors, you see the same theme. So you have from David Wallace, Bell's theorem requires that from her, so Alice's perspective, her distance experiment also has a definite outcome. This is not the case in Everettian quantum mechanics. We have from Brown-Timson, there's no question of the obtaining of one definite value of spin at one side, forcing the anticorrelated value of spin to be obtained at the far side. Both sets of values become realized. And from the 2020 paper by Kai and Kevin McQueen, we have even the explicit form of a single world assumption, which says there exists a single world ontology in which every measurement has a single definite outcome. So the common theme is single world assumption concerns factual status of Baire correlations, and therefore I think it could be stated as there factually are non-separable correlations F between the outcomes at space-like separated locations. And potential preconditions for this could be that we actually see non-separable conditional distribution of outcome records at a single site. So thinking again of this branching picture, we see this, and if we see this, we might think that it also happens at the separable sites. If we believe something like unique records, that observations produce unique records, there might be more assumptions there. There might be more general, better assumptions which are more fundamental. This is like first approach to this, and then. You see there's more room, more white space here. One can then change this a little bit and instead of calling this single word assumption, we have this factuality of Baire correlations here with these two preconditions, that we have this recorded correlations at a single site, and that then we believe that observations produce unique records, and then those together give us Bell correlations. And now we can say, yes, the bare interpretation says, okay, we only think we have any recorded correlations. We don't have nothing. It's an illusion essentially. And the local branching would say, yes, we don't have the unique records. Both the records are at both sides, and they only get correlated later. And at least on the perspective of the word, Lev's interpretation seems to affirm it, the Bell correlations, but then be, in this sense, have action at a distance. So my conclusion would be, there indeed are manifest different causal stories told by the variants of the many world interpretations. The function of the single world assumption in Bell's theorem seems to be to deny the factual status of the non-local Bell correlations. Further work, which I would also like to pursue at some point, would be work towards a more and more complete set of minimal assumptions of the Bell theorem to account for more and more interpretations, options. We also just had the discussion outside whether there could be one where even operationalists and realists agree. It was met with skepticism, but one can dream. And yeah, so what in the paper of 2020 by Kai and Kevin McQueen, there was the aspect that the Bell theorem is not only a no-go theorem, but if the list of assumptions is complete enough, it tells you reliably what you have to dismiss, but it also tells you a nice set of consistent assumptions you can have, and you could try to build theories from this even. And last thing, maybe the elephant in the room is that maybe one could also think of reformulating the Bell theorem further to accommodate alternative concepts of explanation, because what I did not mention so far is how does explanation work in David Wallace or Simon Saunders' version of Bell's theorem, or also how it works in Lev's version, not on the word level, but on the universal level, because also on this level of description, one should be able to make sense of Bell's theorem. And Brown and Timpson, so this is just food for discussion, write very pointedly, in our view, correlations which violate factorizability whilst yet arising from a dynamical local theory need not to be condemned, to be unexplainable. We just need to free ourselves from a Reichenbachian common core straitjacket of what suitable explanation could be. And I'm just wondering whether a consistent formulation of the many worlds interpretation requires, in this sense, to rethink the concept of explanation. For example, to have some concept of explanation based on non-separability, which is an alternative to the Reichenbach principle or something like this. Okay, thanks a lot. Yeah.
Thanks for the talk. Just to be an advocate of local branching, I'd like to say that the story of local branching that really insists on the importance of Alice and Bob recombining in the future in order to compare data is not just a contingency. It's not just a, oh yes, but we can do without it. It's a very important aspect. And let me tell you the story of special relativity. If Alice stays on Earth and Bob travels in the galaxy very fast, while he's still very far, I can ask, who's the youngest? But then any trained person will say there's no definite answer until they remerge and they rejoin. Because if Bob has been traveling on a modest rocket, and then Alice jumps in a very powerful rocket, she goes to Andromeda, and then she goes to meet Bob, she'll be the youngest. So at the moment that they are space-like separated, there's just no meaning of who's the youngest, who's the oldest. And this is very akin in the Bell scenario. And so far as they have not recombined to compare data, there's no correlation, there's no such thing to say. So that's just sharing a thought that it's not actually a specific property of the Bell scenario.
So you think that it's even inconsistent to believe that without this joining there are correlations already? That this is, so you deny essentially the factuality of Bell correlations, that there exists these correlations between these two non-local sites before they meet. If I understand correctly, yeah.
There's no such thing as those local common correlations.
In every given Lorentz frame, there is a well-defined concept of who is younger.
Yeah, but it's not Lorentz invariant.
Yeah, thanks for the nice talk. I'm a bit worried that you haven't eliminated the correlating explanation because it's still falsified, even if you don't have the single word assumption. I mean, if you go to the picture where the correlations only exist at their common future, I mean, it's not a direct cause from one to the other. It's still a common cause caused by the quantum state, and the correlation state just don't factorize. I mean, at least in the intuitive level, I think everybody would agree that the cause of the correlations is that they measure an entangled state, no?
That might be so. I'm not sure exactly how this works in this local branching, but just because you don't need the correlating explanation doesn't mean you have to get rid of this principle. You don't have to deny it. You can still. The point is that you can consistently still hold on to Reichenbach's principle and to say that, because you say in this case you just have a common causal explanation. So you don't need to, so you satisfy Reichenbach's principle because you say you have a common cause.
Oh, no, I have a common cause that didn't correlate, didn't factorize.
Okay, that's what you mean. Okay, yeah, okay, I understand. Okay, because you don't have a statistical, you don't have, okay. And for the for the local branching, okay. Yeah, I admit that was not clear for me. So, but then it seems to me more maybe too costly. I mean, because I mean, we would like to solve this contradiction with at least violating at least of assumptions as possible. So when this could also be like a metric of which interpretation is more costly than the other. So as I said, so my intuition would be that you should be able to, or the question, are you able to get to just deny the single world assumption and preserve Reichenbach's principle fully?
Practical social scientists, assuming that if there's a correlation on the face of it, there's got to be factorizing common cause or one's causing the other, and the EPR correlations are just a counterexample to that. I mean, so at a prima facie level, you've got to say something about that.
Okay, but I think we agree that there are formulations where I mean, in Bohmian mechanics, it's not a problem. You have them.
Bohmian mechanics upholds it.
I'm more interested in what positions can be consistently held than singling out a favorite.